Okay, let me start now. Thank you very much for the introduction. Today, I'd like to talk about some early universe physics. And this talk is based on my previous works, collaborating with Satoshi Shirai at IPMU, and more recent work collaborating with Andreas Lindwald at DAISY and Carlos Tamarit at TUM Garching. I think the paper will appear on arXiv soon. So this talk is about the early universe. So we know that the present universe is made of relics from the early universe, obviously, such as baryons, dark matters, and radiations. So these relics are produced at some point in the early universe and evolved until today, which is observed now. And during the evolution, there are several events in the early universe, such as electroweak phase transitions, QCD phase transitions, and Big Bang nucleosynthesis and neutron decouplings, and so on. And well, in order to estimate the abundance of these cosmological relics, we have to know this precise evolution of the early universe. Now, cosmology is getting more precise, thanks to the development of the various cosmological observations. For instance, the measurement of the abundance of the dark matter is now measured as accurate as this formula in the latest Planck result. And now the observational error is just less than 1% or order 1.1%. Furthermore, in the future, we also expect that other cosmological observables are measured very precisely. For instance, I will talk about the gravitational waves, and the far future gravitational wave detector, which is called the arithmetic DeSigo, is expected to be have a sensitivity in the tensor to scalar ratio R in the order of the 10 to the 5. And in the context of the standard slow inflation with a large field, this accuracy, this precision is as good as the order 1%. So in order to compare the theoretical result with this precise result of the observations, we need to make also the theoretical calculations precisely. So in order to estimate the relic abundance, we need to solve the cosmological evolutions. And there are two relevant equations. One is the Friedmann equations, which determines the expansion history, expansion rate of the universe, and depends on the energy density of the universe. And the other is the conservation of entropy, which also fixes the number of the cosmological relics. And for energy density of radiations and entropy density, we usually determine these contributions in terms of the function G star rho, and G star S. And we can use these quantities to estimate the relic abundance of some cosmological observables. So the purpose of this work is to revisit the estimation of these G star quantities, G star rho and G star S, or the equation of state for radiations. And we would like to update these calculations by taking account of the effect of the particle interactions And also we want to clarify the present uncertainties on the estimation of these quantities. And we also would like to study the impact of these calculations on some cosmological observables, which might be used to probe the physics beyond the standard model. Here we focus on the two topics. One is dark matter, and the other is primordial gravitational waves. The contents of my talk is as follows. So we just finished the introductions, and in the next few slides, I'd like to discuss about the thermodynamics in the standard model and some improvement in the calculation of the G-star. Then after that, I will briefly discuss about application to the calculation of the WIMP dark matter abundance. And after that, I'd like to talk about the primordial gravitational waves, which is predicted in some theory beyond the standard model. Then I will summarize. So let us start from the standard model thermodynamics. Well, the naive estimate of the G-star functions is based on the ideal gas pictures, which is given in the standard textbooks in the cosmology. And we can estimate these G-star functions by using this formula based on the Fermi-Dirac or Bose-Einstein distributions for elementary particles. And once we know the mass spectrum of standard model particles, we can substitute it to this formula, and it is straightforward to estimate the G-star function. The result is shown in this figure. So the naive expectation is that there is a change in the effective degrees of freedom at the temperature corresponding to the mass of the particles, because at that temperature, the particles becomes relativistic and contributes to the relativistic degrees of freedom. Well, this estimate is fine as long as we do not want to estimate cosmological quantities precisely. But if we want to make things precise, we may want to go beyond this naive estimate. Indeed, all the standard model particles are interacting, so they cannot be the ideal gas. So there should be some deviation from this ideal gas picture. And the question is how large the deviation is. And there are several developments in the various calculations in the thermodynamic quantities in the early universe that includes the effect of particle interactions. And this slide shows a list of the relevant topics and references. So first of all, there's an improved calculation about the neutron decoupling, which take account of some non-thermal process and determines the value of the G-stars at the lower temperatures. And there are some precise calculation of the perturbative QCD and electroweak theory. So according to these literatures, some dynamic quantities in QCD was estimated up to the 6th order in the weak coupling expansion. And electroweak theory is also determined up to the 5th order in the weak couplings. Furthermore, there are some non-perturbative calculations based on the lattice. And these calculations are relevant, important to determine the thermodynamic quantities around the QCD and electroweak phase transitions. So then here I'd like to combine all these results and update the estimate of the G-star function. So let me look at the neutrino decoupling first. So the neutrino decoupling is relevant around the temperature of the universe around the order 1 MeV. And at that time, there is an annihilation of the electron-positron pair, and there's a change in the G star from the gas of the electrons, positrons, neutrinos, photons, to the low temperature gas of the neutrinos and photons. And neutrinos are decoupled from the thermal burst around these temperatures. Then the most naive estimate is based on the so-called sudden decoupling approximations, which leads to these values for the lowest temperature, lowest value of the G stars. But according to the improvement of the calculation of the neutrino decoupling, according to this paper, we can slightly improve this calculation. So the most important consequence is there is a shift in the value of the G stars at the lowest temperatures, and this occurs due to the fact that they include the quantum electrodynamic corrections and some residual interaction of the neutrinos with electromagnetic plasma. And sometimes the former quantities are also represented in terms of the effective neutrino degrees of freedom and effective. And this is slightly larger than the 3. And this slight deviation might be probably in the future precise assumed estimate. After all, this improvement is just of order 0.5% in terms of G star. So it might be not so big, but according to the sensitivity of the future cosmological observation, it could be relevant. Well, the more important thing is comes from the estimate of the QCD. This figure shows the pressure of the QCD normalized by the ideal gas result, and in terms of the function of the temperature. And in this regime, we can estimate the pressure by considering 3 different regimes. First, at the lower temperature, we can consider the system as a gas of the free hadrons. And using this picture, we can estimate the pressure, which is shown in this black line. But this picture breaks down at some point at high temperature, and we have to switch to the non-perturbative calculation of QCD. Nowadays, the results of the 4-flavor lattice QCD are available up to the temperature less than 1 GeV, which is shown in this green line. So we can use this result to estimate the pressure at intermediate temperature. Then we have to match this non-perturbative result to the high temperature result based on the perturbative QCD. But unfortunately, it turns out that the perturbative result shows a poor convergence in terms of the thermodynamic quantities. As shown in this figure, the results can differ, fluctuate a lot, the order by order, and there's no obvious convergence around this temperature range. So this slide explicitly shows the result of the perturbative calculation in QCD taken from this reference. And for value of the strong coupling at the temperature of order 1 GeV, we can immediately see that the results are not converging, which leads to the biggest uncertainty for the determination of their effective degrees of freedom in the standard model. Furthermore, it is known that there is some unknown contribution at the level of the order alpha S2 cube, which is related to some fundamental problem in the thermal field theory known as the Linde's problem, that all higher loop contributions turn out to be of order alpha S cubed. And one cannot estimate this contribution in the perturbative expansions, and one has to rely on some non-perturbative estimate. And this contribution is parameterized by some unknown parameter QC, and we can substitute any value here to estimate the pressure of QCD. And this leads to additional uncertainty of the pressure at the higher temperatures. Well, compared to the QCD calculations, the calculations of the electroweak crossover is quite precise. So this figure shows the estimation of the energy density and the pressure around the electroweak crossover calculated by this reference based on the lattice calculations. And green band corresponds to the error of the calculations, and it turns out that it is less than 1%. On the other hand, the uncertainty of the QCD, of the higher order QCD, turns out to be as large as order 1%, even at these high temperatures. So compared to the QCD uncertainty, we can say that the uncertainty from the electroweaks crossover is minor and well under control. So we have combined these all the calculations and estimated the full equation state at arbitrary temperature in the standard model. And this figure shows some result. So the dotted line corresponds to the ideal gas approximations, and blue line is our updated result. And blue shaded lines is our conservative estimate on the uncertainties from the calculation of the pressure. So we see that there are some deviations from the ideal gas results, and it becomes largest at a temperature of order 1 to the 10 GeV, and it is as large as 10%. So it may also affect the calculation of the cosmological relics. And another interesting result is that convergence to the ideal gas result, which is commonly given by used as a 106.75, is fairly slow even at the very high temperatures. So even within the standard model, the value of G star is slower than the naive value at the very high temperatures. And these results can be straightforwardly understood in terms of the perturbative expansion of the pressure. So we may expand the pressure as a function of the coupling constant and the leading contribution the G order G squared. And by substituting the result of the QCD, we see that this amounts to the shift in the G star of order 1. So there's some order 1 difference from the ideal gas result. So we can use this deviation also leads to some uncertainties on the cosmological relics. By the way, we can make this data available online. So you can download it from this URL and use it for whatever you want to calculate in the cosmology. So this is the end of the discussion of the standard model thermodynamics. And in the next few slides, I will briefly discuss about some application on the dark matter abundance. So here we just focus on the simplest scenario of the WIMP dark matter, where dark matter particles annihilate to the standard model particles, and the abundance is determined by the standard freeze-out mechanism. So at some point, the dark matter decouples with a thermal bath, and its number is frozen, and abundance is basically given by the annihilation cross sections. And the relevant equation is as follows. So we can solve the Boltzmann equation of the annihilating dark matters, and we can derive some analytical solution from these equations and estimate the dark matter abundance, which is given by this approximate formula. And according to this formula, the abundance depends on the value of G star to minus of 1/2. And this G star should be evaluated at the freeze-out temperature of dark matter. And the freeze-out temperature of dark matter is related to the dark matter mass, and it is slightly lower than the dark matter mass by a factor of order 10. So basically, the uncertainty of the G star at the 0.1 times dark matter mass will affect the dark matter abundance. And we did some very simple exercises to estimate the dark matter abundance. So we numerically solve the Boltzmann equations and revisit the estimation of the dark matter annihilation cross sections. And this shows the result. So y-axis is we assume the S-wave annihilating dark matter. So this is the S-wave cross sections. And y-axis is the dark matter mass. And this figure shows the annihilation cross sections that explain the observed dark matter abundance. And we, as expected, we see that there is some uncertainties on the estimation of the annihilation cross sections, and this is just 5%. But it might be relevant in the future dark matter searches if it will reach the precision of the order 1%. And we also compare the various previous calculations, results of the previous calculations. And so different authors uses a different estimate on the QCD equation state. So at the most, there is a 8% difference according to which QCD equation state were used. So this kind of uncertainty still remains and may be relevant in the future dark matter searches. Okay, so the later part of this talk, I will discuss about the primordial gravitational waves. So the primordial gravitational waves is an important prediction of the inflationary theory as it originates from the tensor type fluctuations produced during inflations. And the spectrum of gravitational waves is usually parameterized by this quantity omega GW, which is the ratio of the ratio between the energy density of the gravitational waves in the logarithmic interval to the energy density of the critical energy density. And we can further decompose this result into the two factors. One is the primordial tensor power spectrums, which is determined basically from the dynamics during inflation and contains the information about the inflationary models. And there are additional factor, which is called the transfer functions. And it describes how gravitational waves evolved after they enters the horizon. And it contains the information about the summer history after inflation. And we have to know both quantities in order to estimate the spectrum gravitational waves observed today. So here's the basic equations. So we can describe the gravitational waves as spatial metric perturbations. And from the linearized Einstein equation, we can derive this equation of motion for the metric perturbation. And we may decompose the solution in the Fourier space as the two factors. One is the initial amplitude, which can be related to the primordial tensor power spectrum, and its amplitude is determined from the inflationary scales. And we can also factorize how gravitational wave propagates after Poisson crossing by this factor, and this can be translated into the transfer functions. So after all, the gravitational wave spectrum is given by this formula. So the time evolution of gravitational wave after inflation times some inflationary scales. And we can determine the time evolution by numerically solving this evolution equation of gravitational waves. And this slide shows a rough picture of the evolution of the gravitational wave modes in the inflationary cosmology. The y-axis is a log of the length scale, and x-axis shows the log of the scale factor. And this white line describes the evolution of the horizons, and this orange line shows the evolution of the gravitational wavelengths. And at some point in the early epoch, the gravitational wave is produced. And since the horizon is constant during inflation, so the modes crosses outside the horizon at some point during inflation, and the amplitude is frozen. But after the end of inflation, the horizon grows with time, and at some point, the gravitational waves cross the horizon and enter the observable universe, and start to evolve as a usual radiations. Then, we can describe the gravitational wave with a characteristic time, which we call the horizon crossing time. And the frequency of gravitational waves is related to the Hubble parameter during inflation, Hubble parameter at the horizon crossing. So it implies that the higher value of the higher frequency gravitational waves corresponds to the mode that enter the horizon at the earlier epoch in the early universe. And let me further explain the evolution after the horizon crossing. So the time evolution of the gravitational wave amplitude can be described by this formula. So we can take the logarithmic derivative of omega GW and decompose the result into two factors, two terms. So one is the derivative of the energy density of gravitational waves. And after the horizon crossing, this is just 1 minus 4 because it restricts the radiations. On the other hand, the derivative of the critical energy density of the universe is parameterized by the equation of state of the universe. which is defined by this equation. So in the end, the amplitude of the gravitational waves is given by some integral of the equation of the state parameters after the horizon crossing time, multiplied by the amplitude of the gravitational waves at the horizon crossing. And the amplitude at the horizon crossing is roughly given by the primordial gravitational wave amplitude. And in the radiation-dominated universe, we can further simplify these equations. So in this epoch, the energy density of the universe scale as a G star rho times 10 to the 4. And by using the conservation of the entropy, this can be related to the scaling factor times G star S of the -4/3. Then we substitute this scaling relation to this formula and find that this reduction function is given by some ratio of the G star functions. And if we compare the amplitude of gravitational waves at different frequencies, it is proportional to the integral of equation state between these two different horizon crossing time, or the ratio of the G star values at these two different horizon crossing times. So we see that there are if there is some deviation from the pure radiation equation state, 1/3, or constant value of G star, then we expect that there is some deviation from nearly flat spectrum due to the primordial tensor spectrum. This figure shows the result for the standard models for broad frequency intervals. So as I mentioned before, the frequency of gravitational waves is related to the Hubble parameter at the horizon crossing. And in the radiation-dominated universe, we can estimate it in terms of the temperature at the horizon crossing. So there is some one-to-one correspondence between the frequency of gravitational waves and the temperature of the universe at the horizon crossing. So we can show the spectrum of gravitational waves as a function of the horizon crossing temperature, as shown in this top panel of this figure. And we expect that various cosmological events are imprinted in the spectrum of gravitational wave spectrum. So in this sense, the gravitational wave spectrum represents a movie looking into the early universe. So in principle, the observation of the gravitational waves at the different frequencies can see the universe at a different time, different epoch. Unfortunately, however, it turns out that it is difficult to observe these standard model features in the future observations. For instance, the frequency range of the 10 to the -9 to 10 to the -8 Hertz will be probed in the future pulsar timing observations, such as EPTA or SKA. But and this frequency range is relevant to the feature from the change of the equation state at the QCD crossover. But unfortunately, the expected sensitivity of the future observations is still above the expected amplitude of the gravitational waves predicted in the simplest standard inflationary models. Well, on the other hand, recently we found that there's some interesting predictions obtained from some class of the minimal extension of the standard models called the Standard Model-Axion-Seesaw-Higgs total inflation model, which is proposed by these authors. So we see that this model leads to some important, interesting consequences on the future observation of the gravitational waves. This model is proposed based on the simple extension of the standard model, just by adding a few field contents to the standard model framework. And it can address five fundamental problems in particle physics and cosmology, including inflation, baryon symmetry, neutron masses, dark matter, and strong CP problem. And if we actually require that the model should solve these five problems simultaneously, it constrains the parameter space of the model. And because of its constraint framework, this model provides definite predictions for various cosmological observations, including the CMB and action dark matter experiments. So now I'd like to focus on the gravitational wave spectrum predicted in these models. This is a brief explanation of the model setup. So this model is constructed by adding a new complex singlet scalar, sigma, right-handed neutrinos, which gives a mass to the right neutrinos via the usual seesaw mechanism, and may lead to the baryon leptogenesis. And also introduce a vector-like quartz, which is charged under the human Peccei-Quinn symmetry. So this model realizes their action models with a KSPZ formulation. And this model describes the inflation via the dynamics of the Higgs field and this additional scalar field sigma. If we introduce some nonlinear coupling to gravity, then it helps to make the potential flat enough to make the slow roll inflation compatible with the observations. Furthermore, this Peccei-Quinn symmetry breaks spontaneously, and after that, actions arise at Goldstone bosons and becomes the main constituent of dark matter. And the scale of the symmetry breaking might be related to the action decay constant. And this decay constant might be fixed by the requirement of the action dark matter abundance. Well, one important prediction of this model is about the critical temperature of the Peccei-Quinn phase transitions. So this model predicts the second order Peccei-Quinn phase transitions, which happens at the critical temperature given by this formula. And it depends on the various coupling parameters in the theory. But if we impose several constraints from other cosmological evolutions, then it will lead to some definite predictions. For instance, if we require that inflation occurs successfully, then the value of the self-coupling of the Peccei-Quinn scalar is constrained within this range, 10 to the minus 13 to 10 to the 10. Furthermore, if we require the condition of vacuum stability, then the amplitude of Yucca couplings and Higgs boson coupling is constrained and roughly given by this formula. Finally, if we require that actions are main component of the dark matter, then it fixes the Peccei-Quinn scale. And here we take FA to the 10 to the 11 GB to explain, which is a canonical value to explain the observed dark matter abundance. And once we assume these values, then above formula leads to this estimate of the critical temperature of the Peccei-Quinn phase transitions, which is order of the 10 to the 8 GeV. And this temperature range is very important for the gravitational wave observations. So what we expect is that there is a change of the equation of state around the critical temperature of the Peccei-Quinn phase transition. And we can estimate this effect by using the effective potential of the Peccei-Quinn field at a finite temperature. And this figure shows the result. We see that there is a step-like change of the G star, and corresponding to the decoupling of the heavy degrees of freedom, such as sigma field and some additional heavy baryons. And at the lower temperature, the plasma is made of the standard model plus actions. And this happens at the temperature correspond to the 10 to the 8 GeV. And in terms of the frequency of the gravitational waves, it corresponds to order 1 Hertz. So we expect that some features in the gravitational wave spectrum on these frequency ranges. So this figure shows the comparison between the theory predictions with the gravitational wave, future gravitational wave experiments. Colored lines correspond to the prediction of the mesh model. Here we introduce a 4 benchmark points corresponding to the 4 different choices of the model parameters. And the blue line roughly corresponds to the highest value of the gravitational wave amplitude consistent with the observations. And the lower red value corresponds to the lowest possible value predicted in this model, compatible with some theoretical requirements. And if we compare with the experimental sensitivities, we see that in the future gravitational wave experiments are sensitive to the gravitational waves at the frequency range above the 10 to the minus 1 Hertz to the 10 Hertz. And the relevant experiments are D cycles or BBO. Below these frequencies, there are some huge contaminations coming from the extragalactic white dwarf binaries, and it makes it impossible to detect a signal below the frequency ranges below the 0.1 Hertz. But above these frequencies, in principle, one can measure the gravitational wave amplitude directly via the future gravitational wave spaceborne experiments. And in principle, we can further improve the experimental sensitivities up to the noise limited by the quantum noise. And in the past, it was argued that in principle, one can reach the experimental sensitivity as low as the omega, as low as the 10 to the minus 20 in terms of the omega GW. And this ideal experiment will be called the ultimate decimal. And if we actually have such kind of ideal experiment, it have enough sensitivities to probe the features on the spectrum of gravitational waves, such as a feature predicted in this mesh model. And this figure shows some detailed comparison between their prediction of the mesh model and their sensitivity of the ultimate decimal. So we see that there's some step-like feature in the gravitational waves at the frequency range correspond to the Peccei-Quinn phase transition predicted in these models. And it exactly coincides with the best frequency ranges in proved by the future gravitational wave observations. So, so from this result, we can say that there is a possibility to probe the nature of the Peccei-Quinn phase transition in the future high sensitivity gravitational wave experiments. So this is the end of my talk, and let me summarize. So in this talk, we focused on the estimation of the equation state for the radiations by taking account of particle interactions in the standard model and some model beyond the standard model, and estimated uncertainty of their these calculations. And we find that there is about 5 to 10% uncertainty in the estimation of the WIMP dark matter abundance. And this uncertainty mainly coming from the uncertainty from the QCD pressure. So in order to improve the abundance calculation, the improvement in the QCD pressure of the calculation of the QCD pressure should be important. And we also focus on the calculation of the gravitational wave spectrum. And we find that the non-trivial feature coming from the Peccei-Quinn phase transition in the simple extension of the standard model called the SMESH model leads to the observable feature in the frequency range relevant to the future space-bound gravitational wave interparameters. So we can say something about the Peccei-Quinn sector of this model from the future precise observation of the gravitational waves. So that's all of this my talk. So thank you for your attention.
Thank you very much for a very interesting talk, Kenichi. So we have time for some questions. Who would like to go first? Maybe I take the opportunity actually to go first. Can you go back to slide 10, I think?
Okay. Oh.
Oops. So the slide 10, where the uncertainties were from the QCD.
Sorry, there's some time lag.
Oh yeah, okay. Yeah, perfect. Yeah.
Yes.
So I'm actually a little bit surprised to see that the uncertainty is largest for larger temperatures. What is, do people understand where that's coming from? That it's basically split around the ratio, that some overestimate or some predict a prediction which is larger than the ideal gas for the pressure and some smaller.
Sorry, which uncertainties?
Oh no, so the question is basically there is a split, right? So some calculations basically say the correction to the pressure should be larger than the ideal gas prediction, and some say it's smaller.
Yes. So where one can say about the sign of these corrections. Maybe this is just a coincidence. So if there are some, for instance, this third order or fourth order contributions is positive and their other contributions are negative, but this comes from the formula of the perturbative estimate. Mm-hmm. And sometimes accidentally it can be larger than the lower order. So it's accidentally shift the estimates to the larger one or in the different directions. So,
okay. But it's a little bit worrisome about the corrections. If a higher order correction is larger than the lower order correction, which calls into question kind of the perturbation
this is
theory.
surprising result. But if we take the alpha S to the smaller values, then they gradually converges at the higher temperatures.
Okay. That makes sense. That makes sense.
But in the QCD phase transition, alpha S is relatively large. Then these contributions are compounded.
Okay, thanks. Okay, that makes sense. Are there other questions? So you can just speak up or raise your hand. I'm not sure. I have more questions actually.
I can ask a question.
Oh yes, yeah, please.
Can you comment on some of the other ways we can probe the SMASH model? So either in like the axion sector or the neutrino sector or Higgs or whatever, because you're making, there's a lot of kind of grand claims about solving problems in particle physics. There's presumably other ways that you can test the SMASH model other than just the physics around the phase transition.
Well, another thing is that the tensor mode probed in the CMB. So this model requires that the non-minimal coupling to gravity, and it basically leads to the large field information. So and furthermore, it also improves the unitarity problem of the Higgs inflation, which is problematic if the nominal coupling is larger than order 1. But in this model, the nominal coupling can be smaller than 1 and make the prediction compatible with the observational constraints. And it turns out that it leads to some constraint predictions for the tensor to scalar ratio. For instance, the R tensor to scalar ratio of R is about at most 0.1, and at the smallest it is just order of 10 to the -3 or -2. So this large amount of the gravitational wave should be probed in the future CMB experiments. And the other thing is, of course, the action dark matter. So this this model relies on the assumption that the action dark matter explains the universe, which means that the FA is as large as this value. So if a future action dark matter experiment probes determines the action dark matter mass, then one can in principle distinguish this model and other possible other action models. But regarding this prediction for the action dark matter, we should take account of the uncertainty of the calculation of the action dark matter abundance. And unfortunately, at the moment, there are a lot of there are a huge uncertainty on the determination of the FA from the action dark matter abundance. So up to the estimation of the action dark matter abundance calculation, then there might be some different consequences on the action dark matter experiment and also the interpretation of the model.
What is the domain wall number of the SMASH model?
This is domain wall number equal to 1.
Oh, okay. So there's no, yeah, okay.
So in principle, there should be 1-to-1 correspondence between action dark matter abundance and FA.
What is the value? What is the mass here? Remind me. 10 to the 11 GeV is what?
This is about 10 micro electron volt.
Yeah. Okay.
Like
so it's like an ADMX range.
Yeah.
Yeah. Okay.
That's good. Are there any other questions?
Yeah, can I ask a question about vacuum stability, the Higgs vacuum? Well, I presumably missed this, but so in this model, the vacuum is absolutely stable, the Electroweak one, or it's metastable still?
Well, it's absolutely stable. So in this analysis, they consider the parameter space where the electroweak vacuum is absolutely stable, and this might be due to some additional contribution of the Peccei-Quinn scalars that changes the renormalization group rank of the Higgs quartic coupling. So of course, it depends on the parameter values. If some value of the Higgs photon couplings are different from this constraint, in principle, Higgs vacuum and also the full potential, including a Peccei-Quinn scalar, becomes unstable. But one can choose some safe parameter space where all the Higgs and the Peccei-Quinn, the full potential, including the Higgs and the Peccei-Quinn scalar, becomes absolutely stable up to the Planck scale.
Yeah, okay. Is that the stability achieved with this tree-level contribution or through the loops? Because this Peccei-Quinn scalar is heavy, isn't it?
Yes. Well, so there in this paper, the stability condition is checked up to the one loop level. So one loop contribution is also included.
You mean one loop in RGEs of running? Is that?
Sorry, what is the question?
Well, I mean, you know, the RGEs presumably is not that much. I mean, it's a logarithmic running for heavy scalars. I would assume that it comes from the kind of you know, the different definition of you know, self-coupling, you know, because of the mix.
That's true. Yes. So actually, actually the Higgs self-coupling at the low energy is different from the quartic couplings at high energy because of some additional contribution from the Higgs photon couplings. So there's some matching conditions between the low energy Higgs quartic couplings to the high energy Higgs quartic couplings. And according to the value of these photon couplings, this matching condition can improve the stability of the.
That's happened already in classical level, right? At classical level.
Mm-hmm.
Yes, that's already in classical level.
Okay, so I think since we are already past the hour, I would say we thank Kenichi once more for a very nice talk. Kenichi still has some time to answer more questions.